Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review for those who are entering integral calculus. If you are entering this course, you should already have seen actual integrals in your Calc 1 class. However, it's likely been either a winter or a summer, and you've likely forgotten a lot of the background theory that's critically important as you step into your Calc 2 course. So that's what this video is here to do, to backfill that information so that your professor or your instructor does not have to actually spend too much time talking about that. So let's talk about what we learned in Calc 1 that is so necessarily important in Calc 2 to understand from day one. And that is specifically the idea of a Riemann sum. Now let's pretend for a second here that we have this x-axis or horizontal axis, if you don't like me using the variable x, and you have some function. That function could lie above or below the x-axis, but for the purpose of this video, I'm just going to make it lie above this x-axis. It goes on indefinitely in both directions, that doesn't matter, and it's a function, so it passes the vertical line test. That last part is actually very necessary for this theory. What we're going to do is we're going to try to find the area, the signed area is what we call it, the signed area underneath this curve from some point x equals a, or some x value a, to some x value b. So again, our whole purpose here is to find the area underneath this function, which I'll actually call f of x, but still the area lying above the x-axis, so between the function and the x-axis. By the way, if the function actually dipped below the x-axis, let's just pretend that's what it looks like, we'd still say we need the signed area between the function and the x-axis. So you'd want to know what this area is, what this area is, and then what this we would call negative area is. So in reality, that the sum of those three areas would actually be negative because you have more of a negative area or an area below the x-axis. That's just a heads up there. Now, how you did this in Calc 1 was you went ahead and diced this interval from A to B into n sub-intervals, and they were equally spaced sub-intervals. That's critically important for us in Calc 1 and 2. However, just to give you a heads up, as you move forward in mathematics, if you go into, let's say, computer science or engineering, probably, I don't know if it would actually pertain to engineering as much as it does to numerical analysis and theoretical mathematics, that you are allowed to have different sized slices, different sized sub-intervals as you move forward. But when you're first learning the theory, it's just so much easier to talk about it in terms of evenly spaced sub-intervals. So let me go ahead and spend a few moments just slicing out a few sub-intervals so we can see them. So there we have it. We have our n sub-intervals. I have this ellipses, or these ellipses here, to indicate that these slicing patterns continue on forever and ever. Well, maybe not on forever and ever, but they continue on until we get to the very right edge of this interval. In all, we will have done n sub-intervals, and if they're equally spaced, and if we called the distance or the thickness of each sub-interval something common, let's say a wiggle in something, maybe a wiggle in x. So let's just pretend as though we call this distance here a wiggle in x. Well, we know from our algebra 1 and 2, that a change in distance is denoted by a capital delta, Greek letter capital delta. So there we go. That's a change in x right there. Here is the same size of change in x. And again, back over here, we had the same size change in x. So all of these step sizes is what I would call them. They're all the same size, step size. even this one that's in the middle here, which is going to be very important for us to talk about. So I will go ahead and just denote that that distance right there is also a little wiggle in X. That little wiggle in X, that delta X, will get very, very small if we increase the number of slices. So if we only had 10 slices here, obviously the thickness of each slice would be, well, somewhat thick. But if we had 1,000 slices, they get much thinner. And if we have 10,000 slices, it's even much thinner for each subsequent slice, or for each slice. And you learn in your Calc 1 course that you could take the limit as the number of slices goes to infinity, and that would give you an infinite number of slices here, and we can use that infinite number of slices to get a really good approximation, in fact, the exact area underneath this curve. But the question is, how do you find these areas in the first place? Well, you have choices. So let's talk about this first area here, which I am going to go ahead and denote as area sub 1. In fact, I'll call this the first interval, and this is going to be our second subinterval. Here's our third subinterval. And when you get all the way down to the end here, this is our last subinterval. Now, if we had 10 subintervals, that would be our 10th. If we had 20 subintervals, that would be our 20th. I'm pointing at this one, by the way. If we had n subintervals, this would be our nth subinterval. And the one prior to it would be the n minus first subinterval. There we go. And in the center there, I'm just going to give that an arbitrary value of the ith subinterval. That's the most important subinterval we are going to deal with in calculus. Now let's talk about how to approximate the area underneath one of these slices. And in fact, I'm just going to focus on this first subinterval here, just to showcase the possibilities. So when you were in Calc 1, there were the first two approximation methods that you learned were the right endpoint approximation and the left endpoint approximation. To be very honest with you, the Riemann sum, I'm throwing out a word that I haven't talked about yet, but the Riemann sum is really based mostly around the right endpoint method. But let's talk about that. So you have this interval from A to some value. And you know what? I might as well label that value. Let's call A, traditionally we do, the very first, the leftmost endpoint of your entire interval, we call x sub 0 or x naught. And the next value right there we'll call x sub 1. And the next value for our edge point there will be called x sub 2. And the next one will be x3. And so on and so forth down the line until you get all the way to the rightmost edge, which we call B, obviously, but that's the nth x value. We have actually how many x values altogether? Well, we have this guy right here that's 0, 1, 2, 3, ... all the way to nth. Well, let's talk about what if n were 10, right? So you start at 0 and count up to 10. You've actually counted 11 edges, or 11 x values. So you actually have one more x value than you have number of slices, and that should make sense. Just take a moment and draw any function you want and slice it into two subintervals. These two subintervals right here. You actually have 1, 2, 3 edge points or x values of interest. So again, 2 subintervals leads to 3 x values. N subintervals leads to n plus 1 x values, but we call the very first x value x sub 0, so that way we could end at x sub n. By the way, if that x value right here is b, which is x sub n, then the x value prior to that is x sub n minus 1. The x value prior to that is x sub n minus 2. The subscript notation that we're using, very, very important. Think about also, when we looked at this first subinterval, we started from x sub 0 and we ended at x sub 1. The second subinterval starts at x sub 1 and ends at x sub 2. Notice the right edge point of our subinterval matches the interval number. The third subinterval, its right edge point is x sub 3. The third subinterval, its left endpoint is x sub 2. So these are going to help us define what the x values are for our ith interval, which is this guy right here. Remember, the right edge point of this ith interval is going to have an x value that matches, or an index for the x value, that matches the index for the slice number. So this is the ith slice, so the right edge is x sub I. The left edge is x sub I minus 1. Now that was a lot of conversation without getting anywhere, because we still need to talk about how to approximate the area underneath this very first curve here, or the area of this very first slice. And I said we had two methods we learned in Calc 1. Those two methods are the right endpoint and the left endpoint method. Let me grab my ruler, slide it on over. If we were to use the right endpoint of this interval, and I'll use red here for right. If we use that point right there to give us the y value, so we plug in the x value into our function, notice the corresponding y value is right up here. And if we use that as the height of this slice, the representative height of the slice, then we can approximate the area underneath the curve, at least for that slice, using the right endpoint. And you can see that gives us a nice rectangle. And obviously the area of a rectangle is width times height. So in that case, the area, if we used right endpoints, and again, I'm using red for the right endpoints here, the area of that first rectangle is going to be width times height, width being delta x, height being f evaluated at the right endpoint. That would be the area of that ith slice if you were using right endpoints. And to be honest with you, that area is not a really good approximation of the area underneath that function, right? So this is approximately equal to the true area, which I'll use a bar for true, okay? The true area of that first slice. So the true area that underneath that first slice is different than our approximated area, but all we can do right now is approximate. Now, we also learned how to approximate the area underneath the curve in this first slice using left endpoints. Now, using the left endpoint, that means we're going to use x sub 0 and its corresponding y value, which is the function value here, to determine what the height of our function is, or basically to approximate the height of the function on that slice. I had to break the line there just so that I didn't write over my word first. But anyway, you could see the area underneath the curve can be approximated with this green area right here, which is the area of that green rectangle. So again, the true area, which I'm calling a sub 1 bar, is approximated by this. I'm not going to use a sub 1 because I've already used that, but approximated by width times height. Well, the height in this case is f evaluated at x sub 0, the left edge point. So you have two ways to approximate the area underneath the curve there. First one being using the red right endpoint, and the other one using the left endpoint. Kind of messy if you see it that way, but there you go. One, by the way, is an over approximation in this instance, and the other is an under approximation of the area underneath the curve. Now, as I mentioned earlier, the most important slice that we're going to deal with in calculus is the ith slice. And if you look at the ith slice, it gives us a representative slice that then we can start talking about, well, the general area is going to be. So let's go ahead and talk about, well, what would the area underneath that ith slice be? Or basically, what's the area of that ith slice? Well, if we had used the right endpoint here, then the function value at that right endpoint would be f of x sub I. So the width is delta x, the height is f of x sub I, so the area underneath the curve can be approximated by that rectangle right there. Obviously, that's an over approximation. It's not always going to be the case that right endpoints give over approximations. It's just when the curve is increasing, it is an over approximation. When the curve is decreasing, it's an under approximation. That's something that some instructors have you memorize. I actually don't, but it is kind of a cool little concept. So if I were to use right edge points, the area of the ith slice would equal height times width. Notice I'm saying it the opposite way I was saying it before. Before I was saying width times height, but I like to write height times width. And if you were to add up all of those rectangles, it leads to a summation. Now, because we dealt with the arbitrary ith slice here, we can make a summation very nicely. We could say the right endpoints, if we're using right endpoints with n slices, well, we're just going to add up. That's what the sigma, capital sigma means, is add up all those slices starting at I equals, I was going to say n, but it's actually I equals 1 to n. So we're adding up, starting at I equals 1, going all the way to I equals n, of all of those areas. In fact, I'm going to write it this way, of a sub I. So in this case, if you wrote out that summation, it's the area of the first region plus the area of the second region plus so on and so forth, all the way down to the area of the nth region, right? However, we know what a sub I is. So I could just write this as a summation I from I equals 1 to n of f of x sub I delta x. Perfect. If we had used left endpoints, on the other hand, we would use this x value, and we get that y value right there, which is at the point x sub I minus 1, comma, f of x sub I minus 1, and we get another rectangle, which we could use to approximate the area underneath the curve. That obviously is an under approximation only because the curve is increasing, but that's okay, because as we increase the number of slices, well, that approximation or under approximation gets more accurate. So in this instance, if we were to use left endpoints, again, the area of this ith slice is height times width. Again, height being this guy right here, width being that guy right there. So we get f of x sub I minus 1 for the height and delta x for the width. And we would just want to add up, just like we did before. We're just adding up all these areas from area 1 to area n. Now, of course, we know the formula for a sub I is slightly different than had we used right endpoints. The formula for a sub I, if you're using left endpoints, uses, well, the left endpoint. And there you go. Those are the Riemann sums. That's what they're called. And in fact, any type of summation that involves a product of a function value and a constant, or maybe a variable actually, is called a Riemann sum. There are a lot of different kinds of Riemann sums, but it suffices for us to just say, whenever we hear the phrase Riemann sum, we know it's function times width. Now, I'd be remiss if I didn't mention that there's one other method here, at least one other method that you likely had seen in your previous course. If you've already taken Calc 2, and this might be your second time through, then you have seen that there are a bunch of other methods. In fact, there are entire courses at the upper division and graduate level dedicated to developing new numerical techniques to create faster approximations. And this is very important because this is how the real world works, is through approximations. All right, but let's talk about, well, we use the right endpoint, we use the left endpoint. The next most logical point or x value to use here would be the midpoint. And that's actually the next one you commonly learn. And so I'll use blue for the midpoint here. Obviously, the midpoint is this x value right there. And if you look at its corresponding y value, it's way up here. Rather than plotting the x value or stating what that x value is here, I'm going to save a little bit of space and I'm just going to write the x value in this point right there. The x value is the average between x sub I and x sub I minus 1. And when we think average, we think add them up, divide by 2. So that is the average x value. That's the actual midpoint for that interval. And the function value at that x value is, well, f evaluated at x sub I minus 1 plus x sub I all over 2. And that is the basis of the midpoint rule or the midpoint method. Depends on who your instructor is and how they say it. I say midpoint rule, but midpoint method is just as correct. So let's see how this looks first of all. So it slightly over approximates, and in this case, it slightly over approximates on the left side and under approximates the area underneath the curve on the right side. Well, that's okay. It turns out the midpoint method is really good. It's a very, very powerful method. There is extra computation that you need to perform when you do the midpoint method, but it is still a very, very nice method to use. As far as now that you've just learned these methods, it tends to be a very powerful one. So let's write out the formulas here. So the midpoint rule, the area, the ith slice, is some height times a width. Well, the height of that slice is actually this function value right here. That's the height. So we're going to multiply that height times a common width. Now that we have the area of the ith slice written down, we know that the actual midpoint rule or the midpoint method, if we added up n rectangles, would be the summation I equals 1 to n. So we're adding up a bunch of rectangles, and we would start with area 1, then area 2, all the way to area n, and replacing that a sub I with our formula for a sub I when we're using the midpoint method, we get the following. And there you go. Those are the three major methods that you learned in your Calc 1 course. Now there are some things that I need to mention here. The delta x's, there's a formula for that, and the x sub i's, there's a formula for that. All you really need is a formula for delta x and a formula for x sub I. Once you know a formula for x sub I, you could change that I to an I minus 1 and you will have that guy right there. Or you could add the formula for x sub I to the formula for x sub I minus 1 divided by 2 and you have that whole thing right there. So just a heads up, we're going to move forward and talk about what are those formulas. So here we are. This is the actual definition of the definite integral, which is what we just basically developed, the area underneath the curve. So the actual definition says the following: let f exist on a closed interval from a to b, where this interval has been divided into n subintervals, each having a common width delta x. I actually put here delta x sub I because the reality is a true definition of a definite integral does not require us to have a constant delta x. But again, in Calc 2 and Calc 1, and actually Calc 3, you will always have a common or a constant delta x. We're going to let a, the left edge point of our closed interval, be called x sub 0, and then we'll have a bunch of sample points in between, x1, x2, all the way to x sub n minus 1, and then the right edge point of our interval, our closed interval there, is going to be called x sub n. And that matches what we just put together in the previous page. So those are the endpoints of all those slices. And then we're going to let, here's where my notation gets really tough for students, x sub 1 star, comma, x sub 2 star, comma, dot, 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 all the way to x sub n star, be any sample point in each of these subintervals. Now, before I go forward, I need to really draw your attention to that. When I say let x sub I star be some point in the ith interval, what I mean is that we did not have to use the right edge point, that's x sub I. We didn't have to use the left edge point, that's x sub I minus 1. Nor did we have to use the midpoint, which is x sub I minus 1 plus x sub I, all divided by 2. We could have chosen an arbitrary point in this interval, maybe this point right here. Because it's arbitrary, it's just a point I'm randomly throwing a dart at, but it has to land in that interval, could be the edge point. I'm going to call that x sub I star. It just means it's an arbitrary sample point. And what I could do, theoretically, is use that sample point and the function value at that sample point to give me an approximation for the height of the rectangle for that subinterval. If I move that sample point someplace else, like over here, well then, our approximating rectangle will be different, But as long as we're doing an infinite, or I should say a lot of slices, it's going to really be a good approximation underneath the curve if the function is well behaved. So x sub I star is just an arbitrary value between x sub I minus 1 and x sub I. Could be the actual right and left end or left end points. So x sub 3 star could be this guy right here. X sub 2 star might be this guy right here. And it's x sub 2 star because it's in the second subinterval. And so on and so forth. They don't always have to be placed at the same spot within their respective subintervals. And that's what this definition is saying, is that these x values are just some sample points in the ith interval. And let me go ahead and highlight that, where x sub I star is some sample point in the ith interval. Then we define the definite integral of f from a to b as follows. We're going to use this notation, which is what we call integral notation, definite integral notation technically, to replace our Riemann sum notation when we allow this index in the upper part of the Riemann sum there, that index to go to infinity. So as we allow that index to go to infinity, that is the number of slices to go to infinity, well then obviously your rough approximation to the area underneath the curve starts to become very finely tuned and eventually gets to be an exact area underneath the curve f from the x value of a to the x value of b. You can see there's actually two limit definitions that I use here. One is what I think is naturally understandable, which is that you're letting the number of slices go to infinity. The other one takes a little bit of extra work. What you're doing is you're saying, I am allowing the maximum thickness of each slice to go to 0, which means you need more slices. So they're basically saying the same thing. All right. Notice that this definition is true provided that this limit exists. That is the caveat throughout all of calculus, that some statement is true, some limit statement is true, provided the limit exists and is finite. If it does exist, we say that f is, wait for it because it's hard for me to say this word, integrable on the closed interval from a to b. A is called the lower limit, b is called the upper limit. They're also known as the limits of integration. Now, before we leave this video, I just want to mention the formulas that I almost forgot to mention, which are kind of important, right? So let's go ahead and write those down. I promised you that I would talk to you about the delta x formula, so let's go ahead and just derive that very quickly. If you look at our previous work here, you will see that these delta x's, if we had an interval from a to b and we sliced it into n subintervals, well, delta x should take that full length interval a to b and divide it into n subintervals, just like I just said, right? So it's going to be the distance between a and b divided by n. That's what delta x should be. Therefore, delta x is going to be defined as b minus a over n. That triple equality I often use as meaning defined. And in fact, that is often used in mathematics that way as well. The last piece is to talk about what x sub I is. Now, if you think about it, recall that x sub 0 is just a. And x sub 1 was the next value in line. But if you think about that, the next value, x value that is, in line, well, you could get there by starting at a and going by a single step away from a. So a plus a delta x. And you can actually see that here. To get to x sub 1, you start at a and you add delta x to it to get to x sub 1. Likewise, if you want to get to x sub 2, you could start at a and not just add one step size of delta x, but add 2 step sizes of delta x. And so x sub 2 would be, well, start at a and add 2 step sizes of delta x. And you can kind of see the pattern. X sub 3, you would start at a and add 3 step sizes of delta x. And in general, x sub I, the ith x value in line, would be a plus I delta x. Remember, I here is not the imaginary number, it's just an index. So x sub I is equal to a plus I delta x. I did mention that if you're not using right edge points, which by the way, recall, using right edge points means you're going to evaluate f at x sub I. If you're using left edge points, you'll use f of x sub I minus 1. Well, how do you figure that out? Well, replace this I with an I minus 1. So you would have x sub I minus 1 is equal to a plus, instead of an I, you have an I minus 1, delta x. It's actually pretty quick and easy. So looking at our formulas for the right, left, and midpoint rules or methods, you can see that you can evaluate, for example, the area underneath a curve using left endpoints, because now you know how to compute x sub I minus 1. You could throw that into the function. You also know what delta x is. Likewise, for right edge points, you know what x sub I is, or how to compute it, and you know how to compute delta x. Just throw those x sub i's into the function and compute away. And finally, for the midpoint method or the midpoint rule, you would evaluate f at x sub I minus 1 plus x sub I over 2. While you can actually rewrite that formula and memorize a brand new formula, I probably would not. But if you're interested in seeing the closed form of x sub I minus 1 plus x sub I over 2, well, we know that x sub I, so I'm going to write the plus here, is a plus I delta x. You know that x sub I minus 1 is a plus the quantity I minus 1 delta x, and this is all over 2, and then you can clean this up. If you clean this up, you'll get two a's upstairs. Let's see, an I delta x plus another I delta x, and then minus a delta x, all over 2. I really wouldn't memorize this formula. Instead, if I needed it, I would derive it. It was just that quick to derive. You can technically break this up a little bit and call this a plus I delta x minus delta x over 2, if you really wanted to. As you move forward in mathematics, if you choose to become a mathematician, which I highly recommend, it's a great career, it's very rewarding, or if you go into computer science, again, great career, highly rewarding, you end up wanting to limit the number of computations that you use when doing any type of algorithm. And so what you would do is compare the number of computations for these last two methods there to see which one is actually the faster method, and that would actually be this last one right here. That's, by the way, why you would prefer to do your algebra before you do some coding. You want to clean things up as much as possible, because when you start coding in some programming language, you want to make sure you minimize the number of computations that your computer has to go through. Even though computers these days actually compute very quickly, you are better off pre-computing or at least simplifying your computations so that it speeds up the computations in the long run. Anyhow, that's not the purview of your course, I'm sure, but just kind of a little aside. We are done with this. We have now derived the Riemann sum and the definite integral. We have defined that. And I hope that you do well in your calculus course this semester or quarter, whatever you're in. And yeah, I hope this video is helpful. Have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.